would like to go to our live demo today. And as promised, we will be doing inverse problem solving. In this particular use case, we are to find some mechanical properties of our materials. And why do we want to do this? Well, as many of you for sure know, the material properties in FEM simulation can be very critical. And for example, especially if you have anisotropic materials, it can get very complex very quickly if you try to model every little detail of your design. So what you can do instead is use this kind of lumped approach where you reduce the complexity and find material parameters together for these designs. And the approach is such that we have a measurement. We have done some measurements on the device to get some idea of the behavior, and then we can formulate an inverse problem where we vary the inputs and try to find such inputs that they match the measured outputs. And that is easily done with optimization loop. And in a particular example, we will optimize PCB and some packages on the PCB material parameters for them based on measurements done in a paper by Lee et al., where we basically replicated what they did as an example of what you can do. So with that introduction, let me start the live demo. So as said, this is the original paper by Lee et al. And they made some couple of different tests where they found out the resonance frequency of this design. And in our own work, we replicated the results and got pretty similar results. We did some other simplifications, which explains the variation here. So how do we do this? Well, here is Quanscient Allsolve, and I have opened the demo projects here, where we have this. We published this white paper in Nordpack and prepared this demo, which is available to our users. So what I will do is take a copy of the demo. It will appear here. I have some pre-calculated results here, but we can take a look at them later. So let's rename this to sequential, just to follow it up. Okay, so just a quick intro to the basic interface. Here we have a in-browser, in-app CAD editor where you can do whole designs or just modification to imported step files or GDS files. In this case, we have recreated the whole design with this CAD editor here. Then we have some shared expressions, variables, and functions that you can define by yourself. And then, of course, the materials for the different objects. And then the physics. And here we have only considered solid mechanics, but as you can see in this list, we have a plentiful amount of different ready-made formulations via the graphical user interface. and even more via the scripting. So in this case, we have done very simple, added some clamping, and that's it. The reason why we won't need to consider this so much is that we are doing an eigenmode analysis where we let the object, we have modified the script a little bit. So if you look at here, this is the generated script. So none of this is written by hand. Everything is generated from the graphical user interface setup. But after we have enabled scripting mode here, we are free to do any modifications. And let's make it a bit larger. Here you see that we have this formulation object where you can define your different physics. Here we have only solid mechanics and inertia terms as. So how do we use the API then? Well, to the overview, and to use an API, you would of course need some kind of credentials. And currently we offer API keys for projects. So we can create those keys via the project info here. So let's create a key pair, and I will show how to use this in Linux environment, but we of course have Windows support too, if you need it, and Mac of course. So we want to use environment variables so that we won't store the secret keys in our code file. So here, open the terminal, and I have the code project here. I will just create a simple file to store the environment variables so that I can reuse them if needed. So this file would never be shared. Like this, and then we can enable that. And then we of course need the API SDK package, and you can get that currently from us directly, and later we will have it distributed when it's fully public. So what we need to do is to copy the SDK package, and we will use a Python virtual environment. Like this, and then we activate this environment and install some dependencies, including the Allsolve SDK package. And there, now we have everything that we need to run this simulation via the API. But before we do that, let's take a look at the actual project files. So here we have the dependency, just use some matplotlib and scipy and numpy, of course the Allsolve SDK. And then we have our main file called optimize.py. And what we do here is we read the credentials from the environment, set up the Allsolve SDK with the credentials and correct address here. Then we have here the measured frequencies from the Lee paper. And why do we have them here is, of course, that then we have our objective function for the optimization loop. And what that basically does is start the simulation from our template, wait for until it's done, and then extract the eigenfrequencies, and then calculate the residual from the computed frequencies against the measured frequencies to determine whether they are same or optimal. And what we feed in here is a row, which is collection of the different parameters for the material. So if we, okay, yes, let's put this file, yeah, here. So here we have the code to start the simulation. And first with a copy of the template, set the name for it, and then we set the simulation main script. So this is the script that actually controls the simulation formulation and such. We'll take a look at that soon. And then we select the runtime. Here I have selected just one node with the fast starting node. And here we have our parameters, which you can see are embedded in this one array. So we have the Young's modulus, shear modulus, and so forth. These four first are for the PCB itself, and then these are for the package on the PCB, as you can see, the brown ones here. And then we just start the simulation and return a handle to it so that we can follow the status and so forth. And then let's take a look at the main script here. So this file is basically just a copy of the generated script file we just saw in the UI here. So this here looks very similar, right? And then we have done some small modifications, loading the parameters that we set via the API. And then here we calculate or set up the elasticity matrix based on these several parameters that we are trying to find. And then the rest of it is setting up the formulation basically as we got from the GUI script generation. And then we have some outputs that we set here. We first of all want to output the eigen frequencies, and then we also output the eigenvector real values for the displacement field. So when we run this script, what will happen is that here we call the least squares from the SciPy library, and that will in turn call the objective function with each varied parameter values that we are trying to optimize. And we feed in our initial variables and then the bounds for the variables. So let's run this. Should go just like this. there. You can see that it started as of the optimization loop with these values, and when we go back to user interface, we can see the steps are starting to appear and are running, and you can debug the simulation here, see the visualize the fields. And this, of course, will not look that much like the ones in the paper, as this is just from the beginning of the optimization, but something similar. And looking at the log files, we have some frequencies that are not real, and then the first actual mode is the 7th one here. So we can jump to that. And as you can see, it's you look at this cut from here, it's very similar to the first one here. So the the differences here are due to some variation in the model and the setup. We didn't try to do as much as Lee et al. Did, but it's pretty close, and the eigenfrequencies we get match pretty nicely. So, and one further thing, I can show you the iteration plot. So in this plot, you can see the difference of the shear modulus and this modulus plotted against each other to show what is the optimization trying, and we can see that it's converging in here. And this was sequential, but in addition to that, you can also run such algorithms such as differential evolution, where you can parallelize each generation. I can show you how to do that also. So basically, it's just a different function from the SciPy, and create a pool of the workers. And this is not this is running on your machine, but it's just to all the simulations that will run in the cloud. And with this, it will start a number of simulations parallelly and test the whole. And I have a, if we look at the convergence map, you can see that this ran for quite a while. You can see that it's trying much more widely and still converging to the same spot here as the least squares. So in this particular problem, this probably did not make much sense, but it's very useful in more complex cases.